I'm very, very happy to introduce our speaker today, Dr. Clara Nellis, who works for the ATLAS experiment at the Large Hadron Collider at CERN. And Clara, well, now let me start off with ATLAS. ATLAS is a huge international experiment which involves people from all the continents. Europe, of course, as you'd expect from CERN, but also North and South America, Asia, Australia, Africa. There are universities from all of these countries that are part of the ATLAS experiment. So it's an international collaboration to try to find out more about what the universe is made from. And so Clara is going to be telling us about this, but her own experience is really exemplifies this. She took her PhD at Manchester University. She then went to Paris as a researcher, and then she went to Göttingen in Germany, a very famous university, a lot of great people associated with it. And then she's currently based at in the Netherlands and in Nijmegen, and with all of this, she's working at CERN with the experiments at CERN. She'll tell us more about this. As well as this, Clara is very interested in diversity and inclusivity in science. So that, again, is perhaps something that people might be interested in talking about. But with that, I think we could welcome our speaker.
So thank you, Martin, for that very nice introduction. Yeah, so I'm going to launch straight into this talk. So I know we have a Q&A session at the end, but if anything that I say along the way is too confusing, if I've lost you completely, please let me know and we'll go back a little bit. And I want to make sure that everybody comes along for the whole talk, because I've been assured that there's one theoretical physicist in the audience today and everyone else has not quite spent so much time at CERN. Yeah, so thank you very much. And let's get started. So this is CERN. This is an aerial view that was taken a few months ago of the site. So you'll see that actually there's not so many cars there because it was taken during the lockdown. So there's not so many people who are working here at this time. And just to give you a bit of an understanding of where we are. So this is our planet. And CERN is located on the French-Swiss border by the city of Geneva. And if you see when we zoom in, that section in the bottom right is the airport. So that gives you a sense of scale. This is the Large Hadron Collider. It is 27 kilometers long in circumference. And we have 4 major experiments that are based around the ring. So we have CMS at the top. We have ATLAS at the bottom in this diagram, which is my experiment. And then we also have ALICE and LHCb. So we have 4 major experiments because 3 of them are looking for different things. And then ATLAS and CMS are sibling experiments, which means that we are essentially looking for the same things, but we are there to verify each other. So I'm going to talk about the Higgs boson later, but nobody would have believed us if only one experiment found it. So a very important part of our work is verifying results and I've forgotten the word, but like reproducing the results. So that's the point of having 2 experiments, CMS and ATLAS. So this is the LHC, the Large Hadron Collider. So we take protons and accelerate them in both directions around the ring and bring them to collision in the center of our detectors. And so these protons are traveling at almost the speed of light. And when they come to collide in the center of our detectors, then we take Einstein's very famous equation, E equals mc squared, and we use the energy from this collision to create new matter, new particles. And from this, we can create particles that exist in our universe, but are not localized in order for us to study them. So, but we're not doing that right now. So this is what is currently happening at the LHC at CERN. So currently we're in what's known as a shutdown period. This means that we're not circulating beams. The experiments are not running. This was all scheduled long before the pandemic came along. And it's a sort of 2.5 year shutdown period where we perform upgrades on the detector, on the accelerator, and any repairs that are necessary. So as you can see here, it says first beam expected spring 2021. Later, I will tell you that that's now been pushed back a bit due to the COVID situation. So what are we looking for? So this is what we call the standard model of particle physics. This is our recipe book for building a universe. It is all of the matter particles that we know of, which are the ones around the outside of the ring, and all of the force particles that we know of in the center. So we have quarks, which are the ones in the dark blue. So you might be familiar with the up and the down quark. These are the ones that are inside protons, for example. And then in the bottom, we have the leptons. So on the left, it should be the left for everybody, or is it? Yeah, left for everybody. So these are the charged leptons. So the one, again, that you might be most familiar with is the electron. And so with the electron, the up quark and the down quark, you can build a lot of things in the universe. These are very important fundamental particles. But then we also have the neutrinos. These are neutral leptons. So these don't have any charge, any electric charge, but they're very, very interesting because for a really long time we thought they had no mass at all. And then it was discovered that they do actually have a small mass. And so they're really interesting particles that I will now barely mention for the rest of this talk. But there's whole experiments dedicated just to these particles. And then in the center, you can see these force particles that I was talking about. So we have the photon. This one is probably the one you're most familiar with. It's light. It's the particle of light. And we say it mediates the electromagnetic force. So it allows the electromagnetic force to happen. We then have the gluon, which is part of the strong force. And then we have what we call the W and the Z particles, which are part of the weak nuclear force. And then in the center, we have this particle that we were talking about for a very long time, the Higgs boson. And it was discovered in 2012 with the Large Hadron Collider at CERN. And this was very momentous for particle physicists. And we were very excited that we found it. And I'll talk a bit more about that one later. And then also for a lot of these particles, you have their antimatter equivalents. So this is where you have exactly the same particle, but it has the opposite charge. So for the electron, you can have the positron, and that's the anti-electron. But this is what you need to build a universe, most of a universe. So we collide protons, as I said, in the Large Hadron Collider, and protons are not what we call fundamental particles. When I am talking about a fundamental particle, I'm talking about something that doesn't, as far as we know, have any internal structure. So the electron, for example, is a fundamental particle. But a proton is a composite particle built of up and down quarks, held together by gluons, and then sometimes there are other quarks that sort of pop in and out of existence inside of it. And this forms the proton that we use to collide. And then this plot that I put on this slide is to illustrate how many collisions we get per second, because this is quite an important feature of the Large Hadron Collider, is that we need a lot of data. We really need to collect as much data as possible with our device. And so the very, very helpful accelerator physicists have designed the Large Hadron Collider so that the bunches of protons that are accelerated around the ring are very tightly compact in their bunches, which means that as the bunches pass by each other, we get multiple collisions at once inside of our detector. Now this is very helpful if we're looking for very, very rare events, but it's very unhelpful if we want to distinguish which particle came from which collision. So the green section of this plot, for example, is just showing that we got more of these collisions per second, per bunch crossing than we did for the yellow one, which was in 2015. So the accelerator has been improving over time. The accelerator physicists love to try and make it as good as possible, which then challenges us to then make our detectors and our analyses as sophisticated as possible. And so talking of the detector, this is my detector. This is my equipment for doing all of the research that I want to do. It is called the Atlas detector, as Martin was saying. And so to give you a sense of scale, originally it just had these little people on top of it, but I didn't think that was very clear enough. So I've also added a T-Rex. So if anyone has seen Jurassic Park, you then get a better idea of just how big this detector is. And it's made up of many layers, like an onion. So if you can imagine peeling back an onion, that's essentially how the Atlas detector is constructed. It's 44 meters long and 25 meters tall. And even though we're measuring the smallest things that we know of in the universe, we need this massive detector to be able to collect all of those particles that come from the initial collision. So in that movie I was showing you, when the protons collide, a new particle, for example, a Higgs boson, is created, and then it changes, or we say decays, into other particles, and these spray off a bit like a firework in all directions. And so we have to completely surround what we call the interaction point, this center of the collisions, to measure as many of these particles as possible, to then try and understand what particle was there at the beginning. Because particles like the Higgs boson, they don't last for very long. And so we can only infer that they were there from other particles. So it's a bit like a jigsaw puzzle. We have to get all the pieces together to be able to work out what was there in the center. And so here is also just a photograph of the detector that I took one time when I got to go underground. So I don't go underground very often because I'm not, even though I have worked on the detector directly, I wasn't involved, for example, in the installation. But now more and more I'm going underground to show people our experiment. So it's a very nice opportunity to really see the detector and remind myself just how colossal it is. And just to give you another idea, there are 2 people working in this zoomed in version of the photograph, which are in the center of the fisheye photograph. And they're very tiny in the image. So just to show you how really huge this detector is to be able to do our work. And yeah, as Martin was saying, the Atlas collaboration is spread all over the world. So we have over 5,500 members working on the experiment, and it's not just physicists, it's also engineers, computer scientists. We have, well, not lawyers in Atlas, but at CERN we also have lawyers and human resources and support staff, and none of our work would be possible without everybody involved in the collaboration and in the daily workings at CERN. In Atlas itself, we have over 103 nationalities of people working on the experiment. So that's not just institutes or universities that are involved with the research, but people that have come from those countries to different institutes. Like I've moved around to different universities to contribute to this huge experiment. So it's really a global effort. And so this is a nice animation that just shows you how we measure the different particles in our detector. So as I was saying, we have these different layers. And so now we're looking as though we're a proton traveling through the beam pipe, and we're in the middle of the detector, and this is a segment cut out from the detector. And so, for example, we have 3 main sections of our detector. So first we have the tracking detector, which measures charged particles as they pass through our whole detector. Then we have what's called the calorimeters, and calo meaning energy. These measures the energy of particles traveling through, and we have 2 of those. And this is done by essentially slowing down the particles and then absorbing the energy and measuring the energy that they deposit in our detector. And then at the very edge, we have what's called a muon spectrometer. So these muons, as I was showing in that diagram before, are also leptons, but they're essentially electrons, but a bit heavier. But that means that they can travel much further through our detector than an electron can. And we really want to stop those because they're a good signifier of something interesting happening in the center of the detector. A lot of boring stuff happens in those collisions, and we really have to sift through that data to find the interesting stuff. So the muons are very important to measure, and we have a whole detector that are dedicated to them. And then you'll see very faintly on the right of this image a dotted line, and this is a neutrino. So I mentioned those earlier. These are very, very light particles, and they're very weakly, very not interactive in our detector. And so, for example, if you hold your thumb out in front of you, your thumb is roughly 1 centimeter squared, and there are 1 billion neutrinos passing, give or take a few, passing through your thumbnail every second. So that's, and you don't feel them, you don't notice at all. So that's just how little they interact with matter and with stuff. So we can't measure them in our detector. There are detectors, for example, IceCube in the Antarctic, it's either north or south, in Antarctica it's south, that measure neutrinos, but that needs a kilometer squared of ice to measure these neutrinos. So we measure them in our detector by looking, we know that momentum should be conserved. So for example, if there's a lot of stuff measured in one direction in the detector and not a lot of stuff measured in the other direction, we know that it should equal 0 in what we call the transverse plane. So this means that if there's a lot of stuff in one direction and not so much in the other direction, we can infer that there was a neutrino or something else that didn't interact with our detector in that event, in that collision. So this is a way that we determine that there was a neutrino or something else there. Okay, so as I was saying, we have these collisions and they happen 60 million times every second, but only 1 in a million collision is actually interesting to us. So what we do is we take this data that is recorded in our detectors and we send it to some very fast processing electronics. And the fast processing electronics has to make a decision very quickly, hence fast, as to whether this is an interesting event. So for example, it might say, did it have a muon in it? And if it had a muon in it, then it says, okay, we keep this one. That one sounds like it might have been interesting. And then it gets sent on to some more complicated electronics with algorithms that will look at the event in more detail and say, do we still think this is an interesting event? And if it is, it gets passed on. So this is where these cores, these computers are then processing very, very quickly the data to say, is it interesting? Is it not interesting? And then this is all sent up to our data center at CERN, where it is stored from all of the experiments and then distributed across the world so that physicists anywhere with an internet connection can download this data and analyze it for whatever research they want to do. So this is really ideal for us during COVID because we are used to this distributed method of doing research. So I can sit in my apartment at my home desk and still analyze data as though I'm at CERN or as though I'm at my university. So as long as the internet is good and I did have to upgrade the internet, then I can continue working in this way. So we want to find new particles. That's kind of my job. So I can't just go into Google and search for brand new particles and hope that something new comes up. Maybe just quickly one thing to say about the data. So we do this selection of data, but we also have one random selection that saves events very randomly to ensure that if we are biasing our data, if we didn't realize that there could have been something interesting in a certain selection of data, then we can go back and we can look through that data set, which isn't, it isn't as big as as collecting everything, but it does mean that we can check our biases. We can check whether or not we're missing something useful in our data. Okay, so I can't go into your favorite search engine and just search for new particles like that. We have to do it a different way. So essentially what we're interested in is very, very big fundamental questions. What is the universe made of? How did it evolve over time? So we don't really go back to the Big Bang, but we're looking at moments after the Big Bang, when the universe was very small, very dense. How did the particles interact? What was the situation like at that time? So that's mainly the focus of the experiment called ALICE. They collide not protons, but heavy ions. And then they create this massive soup of new particles that exists for a fraction of a second, but they can study them, the conditions at the beginning of the universe, which is very interesting, but not what I work on directly. The big questions that I'm interested in, so the Higgs boson, which was, first of all, we wanted to discover it, and now we want to study it now that we've discovered it. I want to know what dark matter is. So we know that dark matter exists from being able to study the rotations of galaxies in our universe. And there are other experimental methods that have shown that there's more stuff in the universe than the things that I showed you in that nice circular diagram. So we know it makes up about 27% of our universe, but apart from that, we don't know what it is. We're trying to work it out, but it's an unknown. All we know is that it has a stable form. And then there's also dark energy, and really don't ask me about dark energy because we don't know, and I have no idea, except for the fact that it's causing we think it's causing our universe to expand. But that's a whole nother mystery. So often, I mean, I'm a particle physicist, so my bias here is that I want dark matter to be a particle. There are other theories that are available that talk about modifications to gravity or miniature black holes. But for me, I would love if it was a particle. It's something that we could create in our detector and then measure in this controlled environment. But it doesn't just have to be one particle or one type of particle. So our standard model that I showed you was this whole recipe book of different fundamental particles. So it could be, excuse me, that dark matter is a mixture of different things. And it turns out that there's a whole nother recipe book for the dark sector of our universe. But until we start to tease it apart and work out or discover any of these, then we won't know until we measure it. So yeah, I said that there are other ways to know that dark matter is out there. And so one of them is gravitational lensing. So this is a really nice feature that light is bent as it travels through space if there is a large gravitational field. So what happens in this diagram is that if there's a lot of dark matter between Earth and a very bright galaxy, we wouldn't see a perfect galaxy when we looked out in space, but we would see either rings around it or multiple galaxies because the light has been bent around the dark matter. So this is a confirmation that there is something out there, but we can't see it. We don't measure it in the conventional ways that we would measure other matter in space. So one thing that it could be, one of the very tenacious theories that we have in particle physics is called supersymmetry. So as I was, we have a lot of symmetries where you can, so for example, antimatter is a symmetry where we have the same particles, but they have opposite charge. In supersymmetry, we take what's called the spin of the particle. So fermions have a half spin and bosons have an integer spin, and we swap those around essentially. And it's there's a lot more to supersymmetry. It's a very nice theory. solves a lot of issues that we have in physics, but we have to find evidence to support theories. They can't just be beautiful, unfortunately, to confirm that they exist. So this is, it's a very nice, yeah, as I was saying, it's a very nice theory, and the way that we would confirm it is if we would find one of these particles with the properties that are predicted by the theory in our detector. But because dark matter doesn't interact with our detector the way that normal matter does, we have to be a bit clever in how we would measure it. But that's just one possible explanation for dark matter, but until we measure it, we're not sure. And then I was talking about antimatter, and antimatter is very interesting, and we expect that matter and antimatter was equal amounts were created at the beginning of the universe, but there's some sort of asymmetry, some sort of difference between matter and antimatter, because when matter and antimatter come together, they annihilate, they form light. So if you have an electron and a positron and they come into contact with each other, they will form energy, form light, and the matter's gone and the antimatter is gone. So if there were equal amounts at the beginning of the universe, then all of it should have just annihilated together, and would just be a universe of light, which is not very exciting for us, because then we would not be able to exist. So this is a very important feature that allows our existence. I'm very happy about it, but we don't fully understand why it happens. But this is mainly the focus of the experiment LHCb, so that was the one on the bottom right of the diagram that I showed you, and it's not really something I focus on in my research. And then we also have the strength of gravity. So you would think that gravity is very strong. If I fall down some stairs, it's really going to hurt. But I can pick something, usually I have a paperclip in front of me, but I can pick just something up off of the desk, and I am overcoming the whole force of gravity to pick this up off of my desk. So gravity is actually very, very weak force, and we don't know why, and I don't study that in my research because we can't measure it with particles. So it is a very important question, but it's not part of the research that I do on Atlas. But these are just some of the big questions that we're generally interested in physics, or at least my sector of physics. Okay, but now I want to talk to you about something you may have heard of a few years ago or recently. So this is the Higgs boson. So there's a very nice story with a not so very nice politician, so I won't mention who was originally in this story, but I'm going to use the story. You can, if you ever look it up about the Higgs boson explanation, then it was in the 80s, which might give you a hint of who I'm talking about. But the best way to describe the Higgs boson I found in terms of how it interacts. So if you imagine you're at a party, and everybody at the party, all of the people, these are the Higgs field. And if somebody not particularly interesting, somebody new to the party who doesn't know anybody, they can walk in and walk from one end of the party to the drinks bar without interacting with the people, and therefore they're not hindered as they move through the room. But if somebody very famous walks in, then everybody wants to talk to them. Everybody really wants to be able to interact with that person. And that causes, the interaction causes that person to be hindered from getting from one side of the room to the other, which slows down their chance to get a beverage at the bar. If there's, so the very famous person is an example of a heavy particle, and the new person at the party is an example of a very, very light or even massless particle. And then, so this is the Higgs field, so this permeates everywhere. But if there is a rumor of a famous person at the party, then the rumor causes people to clump together and the Higgs field then interacts with itself, this is when you get a Higgs boson. So really, it's the Higgs field that is the interesting thing that we were looking for in particle physics. It was what gives mass to fundamental particles, what hinders them as they move through the universe. But the way to show that it exists is through an excitation, we call it, in the Higgs field, which is this Higgs boson. It's something that we can measure. So if that was too abstract, I also have a video which illustrates the same thing. So this is a universe without the Higgs boson, and everything was moving through the universe at the same speed. And then when we, the Higgs field, sorry, and when we introduce a Higgs field that permeates throughout the whole universe, its interaction with certain particles slows them down and gives them mass. And then the photon, which doesn't interact with the Higgs field directly, then doesn't have any mass and isn't slowed down. And then that's just a nice collision at the end of some protons turning into photons. Okay. Well, no, it doesn't want to. Okay, so that's the Higgs field, and as I said, we want to measure the Higgs boson. So this is what we call an event display. This is an illustration of what it looks like in our detector when we create a particle, and then how it's measured in different parts of our detector. So here we have a candidate Higgs event, so we can never say for sure that it is a Higgs boson, but we think a Higgs was created in the center of our detector, and it is changed into 4 muons. So as I was saying, muons are very, very nice to measure. They have very clean signatures in our detector. It's very clear to see that there was a muon there. And here we have 4, which are the red lines coming from the center of this image to in the middle of the screen. And then that's how it would look for one Higgs boson. But here is what it looks like to a physicist. So we collect the data, which are these black points in the plot. And every time we get a new one at a certain energy or mass at the bottom of the plot, then it increases. The red, purple, and the blue are our predictions, our simulations of what we expect there to be. So the red and the purple were, if there was other explanations for this graph. And then the blue is if there was a Higgs boson, and at the time we didn't know what the mass was. This is going back to the discovery. So what we did is we then looked that there was a gap in this plot, and we put in different simulations at different masses, and found the one that fit the best. And here it was 125 GeV. The GeV is a measurement of energy and of mass in particle physics. And we did this in lots of what we call different channels. So we looked at how the Higgs changed into lots of different types of particles, and we found the same result, 125 GeV. So this was a good confirmation that we had actually found a new particle and not that we were getting some fluctuations in our data. And it's very exciting for particle physicists when we find a new particle. So this was, we announced the discovery of the Higgs on the 4th of July, 2012. And really the atmosphere at CERN was incredible. It was like being, I'm not exaggerating, that it was like being at a rock concert. And as a PhD student who was working on Atlas, I slept outside the auditorium the night before the announcement of the Higgs boson, because I wanted to be in the room to hear it directly from the leaders of our experiments. And so here from the New York Times is a picture of my face clapping as they finally confirm that we have found a new particle. And I told my dad, I sent a copy of this to my dad and said, it's probably the only time I'm going to be on the front cover of the New York Times, unless I do something terrible, which I don't intend to. So we'll treasure this one. And then here, hopefully you get the sound from this. But again, I want to share, because some people will have heard of the Higgs boson discovery, but it was such a momentous occasion for physicists, because it was the culmination of 50 years of searching for this particle. Many colliders, many people had been involved in this discovery. And so then to have the Nobel Prize awarded to the two of the theorists that, that built this idea was a real confirmation of the work that had been taking place.
This year's prize is about something very small that makes all the difference. The Royal Swedish Academy of Sciences has decided to award the 2030 Nobel Prize in Physics to Professor François Anglais at Université Libre de Bruxelles, Belgique, and Professor Peter Higgs at University of Edinburgh, United Kingdom. And the Academy's citation runs for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the Atlas and CERN experiments at CERN's Large Hadron Collider.
So that's what the auditorium looks like when it's very full. That's actually the Building 40 Cafe. When it's full of people, and right now it's very much not full of people. But it was a very nice occasion to mark. So I've talked about the Higgs boson, which is responsible, or the Higgs field is responsible for giving mass to fundamental particles. And I just want to briefly, because I'm aware of the time, talk about my favorite particle. So this is the top, because everyone has a favorite particle. This is the top quark, and it is the heaviest particle that we have discovered so far. It was discovered in 1995. It has the same mass as a gold atom, to give you an idea of just how massive it is. And it has a very short lifetime. It doesn't hang around for very long. I showed you those event displays earlier of a Higgs candidate. Well, this image in the bottom left of the screen is one of the first top pair candidates from the Tevatron, which is the predecessor of the LHC, which was in the US. And they were still drawing it on diagrams. So somebody had to take a ruler, and this is only 1995, but still, they drew it out, and then this was presented in 1990. Oh, this says 1993, but it was for the discovery of the top quark. And one of the reasons that this is such an important particle to understand is because this plot that you see in the bottom right, this tells us about our universe. So we have the top mass on the left, and we have the Higgs mass on the bottom. And that gray triangle or diamond is where we are, or the properties of our universe. And if we're in the green region, everything is fabulous. It means we are in a very stable universe, and the properties of the universe will continue on being the same forever. If we're in the yellow region, it means we're in a metastable region, and it means that our universe could tunnel into a different properties at some random time. And if we're in the red part, then this is even more likely to happen, and it's very bad. But even if it happened, we wouldn't care, because we would just instantly sort of cease to exist. All of our particles would just fly apart. So it's quite a morbid thing, and a friend of mine has written a whole book about the destruction of the universe and the different ways that it can happen, in a very light-hearted and jolly way. But it's an important thing to measure, just to understand more about our universe. And as you can see from the grey triangle, we are currently between the metastable and the stable region. So it's nice to know if we can measure these things. And so this just illustrates a little bit better what the difference between instability and metastability. So I was saying tunneling. So this is the properties of the Higgs vacuum. It's getting quite technical. But in an unstable universe, we would tunnel and then just drop into this instability. And in a metastable universe, it means that we're not our value isn't the most stable that we're currently at, and it could change to a more stable value. But the time and the likelihood of this is much greater than the lifetime of the universe. So I'm not there's far more pressing things that we could be worrying about right now than whether or not the universe is going to cease to exist. But this is a picture of the top quark discovery, and you'd be forgiven for thinking that it was longer ago than the 90s. I don't know why they only took black and white photos that day, but just to give you a comparison for the Higgs discovery. So this was in the US. And then I will go through this very quickly, but it's just to give you a little bit of an idea of what I do on a day-to-day basis as part of my analysis. So I've given you an overview, for example, of what we're doing at CERN, what we're measuring, how we measure it. And my interest is really the top quark, and it changes into a W boson and a B quark a lot of the time, almost 100% of the time. So it has a very distinct signature in our detector. And I want to measure, so for example, in the bottom left, we're measuring how often these top quarks are produced, depending on the energy the LHC has. So we started off at 7 TeV, then we had 8 TeV, this is just the collision energy, and now we're at 13 TeV. So we can plot the measurement of how likely 2 top quarks are to be produced against the energy and compare that to theoretical predictions. And it's very spot on, which is a nice confirmation that we're doing things right. And then what I'm interested in, so if you see this big graph in the center of the slide, is how the top quarks interact with other particles. So W bosons, Z bosons, Higgs bosons, photons sometimes. That's not really my favorite one, but it's still very interesting. And then the one that I've been working on recently is creating 4 top quarks at once. And this, you can kind of get an idea that as you go further down this graph, it's less likely to happen. So these are already very rare events because this graph is on a log scale. So every time you go down, it's a factor of 10 less likely to happen. And so the one I'm measuring is at the very bottom of this graph. So it's an extremely rare thing to measure. But the reason that I want to measure very rare events is because there's 2 ways to discover new physics. So if we want to know what dark matter is, or if there's anything else hiding in our universe that we want to measure, we can either find new particles like we did with the Higgs boson, which was momentous. We had that bump in that graph that clearly said, hey, I'm a new particle, and it's very exciting. Or there's a bit more of the laborious way of doing it, which is to measure every single property of particles in the standard model and to check them against the theoretical predictions. And if there is any deviation from the theoretical predictions, then particle physicists get excited and say, hey, let's look at that one in more detail, because maybe that could show that there's something else happening there that we haven't factored in. So this is kind of the way that I discover new physics, hopefully eventually, is by really precisely measuring how the top quark interacts with all the other particles in the standard model. So I'm going to gloss over this one, but this is what I was saying about how it interacts with different particles. And these diagrams are what we call Feynman diagrams. They're not just pretty pictures or pretty diagrams, but they help us to calculate how likely something is to happen and which particles are involved in the process. So these are just different ways. At the Large Hadron Collider, you can start from the protons, but actually we're going to take the gluons out of the protons and we're going to create top quarks in this event. And so here I've listed that for every 4 top quarks created at once, we get 70,000 pairs of top quarks that are created. So it's a really difficult measurement to do because there's just so much that looks like the thing we're trying to measure. So a colleague once said, it's not like looking for a needle in a haystack, it's like looking for a needle in a pile of needles. So it's really trying to just look for something very similar to everything else that is around you. This is what it looks like as an event display. And this is actually the heaviest particle event. So if you take all of the particles that were created in this collision, it's the heaviest final state that we've measured at ATLAS. So it's a very spectacular thing to be measuring as well. So that makes it a very another reason that it's an interesting thing to study. Okay, and then I skipped some steps because I don't want to keep you all evening, and it'd be nice to actually talk and answer some questions. But we also really have to understand what we call the background. So this is other things that look like the thing we're trying to measure. And maybe those things are because we didn't understand our detector properly enough, or something that was created in the collision is looking like something else. So in this case, I've got an electron that so what I didn't measure when I showed you the detector, what I didn't mention when I showed you the detector is that we can measure the charge of particles because we have magnets in our detector. And the magnets bend charged particles. And if they bend one way, they have a positive charge. And if they bend the other way, they have a negative charge. And sometimes when we're doing our measurement, if we mismeasure that curvature, then it gives us the wrong charge, and then we think it's a different event. So this isn't because we're bad at what we do, it's just that there's a lot of very complicated, lots and lots of information to try and sift through. And we've really been working on what's called big data for a very, very long time. What can help us in analyses like this is machine learning. So we use what's called, in this case, we used a boosted decision tree classification. So we trained algorithms to make decisions for us, because if we do it properly, then the computers can do it better than humans can. And this isn't a very fancy machine learning. It's been around since, I think, the 90s. It's been at CERN a very long time. So people think that machine learning and AI is a very new feature, but actually some of the techniques have been used for a very long time. So a decision tree just takes an input of data and splits it depending on whether it thinks it's the thing we're looking for or not the thing we're looking for. And over time, it can better understand our data. And so in this plot that I'm showing you, the red is what we're interested in. And the nice thing is it's all got a very high score because the score is at the bottom, going from almost -1 to 1. And the higher the score, the more likely it is to be the thing we're looking for. And so these kind of machine learning techniques can help us really sift through the huge amounts of data that we have, and to be able to classify it as different events, different processes that happened from the collision. And then we get our result, and the table on the left is just a whole lot of what we call systematic uncertainty. So we have to be really careful when we're making an announcement of a result to say, did we really understand every single step of the way? And we're so picky within the collaborations. It takes, to give you an idea, it took 2.5 years to do this measurement that I was working on this result, because the collaboration is very conservative in a scientific way, and they won't let us, there's 5,000 people, they won't say, okay, you've got an interesting result, let's just publish that. They say, have you looked at this? Did you consider the modeling, your simulation? Did you use all of the simulation that you should have done? And so we really have to justify every single step of the way. And only when the collaboration is convinced can we then share this result with everyone else. And what's kind of interesting about this result is I didn't really point it out at the beginning, but this number 12 that I highlighted in orange, that's what we expect from the simulations. It's the cross-section, it's how often this event should happen. And then our result, we measured 24, which is twice as big as what we expect. Now, if I could get very excited about this result and say that we're collecting twice as much four-top events than we expect from simulation, and therefore there must be new physics involved. But that's not, we have to be very cautious, and we don't get excited until we have no other explanation. And so at the moment, this is consistent with the standard model with what we call a little bit of tension. So for me, that's great. I love that there's something slightly away from the standard model, and it just means that we've got to keep collecting data. But we call this evidence. It's a measure of confidence to say that, have you discovered this process? And so far we can say we're pretty sure. Until that number hits 5, which is what you might have seen with the Higgs boson, 5 sigma becomes an observation. We we don't confirm. So this might be getting into very, very bitty details, but basically it's saying that if you want to discover something new, or if you want to see if your result is different from the standard model, we have to be really, really, really sure. And we have these levels that we set within our community to make sure that we have tested everything and that we're confident in the results that we're put out. So this is a nice, I'm very happy with this result, and it just means we need to collect more data and see if there's any actual new physics hiding in it, or if it's consistent with the standard model, which a lot of our results are. And so here's that plot again, and you can see in the bottom right now we have this result put on this graph, and this is what I do as a particle physicist. We take measurements, we put them on plots like this, and we compare all of the information that we know about the universe to see if there's anything different to what we expected it to be. And then these are just an array of some of the dark matter models that this could be, if it is true that we are measuring more events than the standard model, but that's too far ahead to say for sure. But it's just to show that we are aware that there are predictions that then could be followed up with this data. Okay, and then I'm just going to summarize with what's next, and then we can hand back, and I think there are going to be some questions. So as I said, our schedule has been unfortunately a little bit delayed due to the COVID. So this diagram in the top left is showing you how we've scheduled whether to run or to perform maintenance over the next sort of 10, 15 years. And it's been delayed a little bit, but in the grand scheme of things, it's really 6 to 9 months is really not that long in a 40-year project. CERN currently looks a lot like this picture in the left. So this is the theory corridor at CERN, although people are starting to return and work is continuing. So this GIF was made before COVID, so no one's wearing face masks, just have to clarify. But yeah, we are now able to access site, and we're prioritizing work that directly has to be done on site, so not work that could be done from home, just to be safe. And then I'm still trying to find dark matter, so we didn't actually discover it yet, but there are lots of places that we can look in the standard model. And one of my focuses of the work that I'm doing at the moment is on more sophisticated machine learning techniques. So I work on something called anomaly detection methods. So it's exactly like the algorithms that they use in banks to check whether somebody is fraudulently using a credit card. So what the banks do is that they take all of the data that they have on their system, and they learn what are normal transactions. And then if a fraudulent credit card, if somebody buys something on your credit card and it wasn't you, if you flag that and say, oh, that wasn't me, I didn't make that purchase, then that helps their algorithms to learn what isn't a real transaction. And then they can start to predict it from the data, and that's why you might get a phone call and say, oh, you spent a lot of money at this shop, you don't usually do that, is that a normal transaction? And exactly the same algorithms can be used on the LHC data. So we can say, this is what the standard model looks like, this is what we expect to see, and then I can run it over huge amounts of data, and it can start to flag up things that look unusual. And often they'll just be, you didn't understand the detector properly, you forgot the simulation of something very mundane. But once we work out all of those bugs, then maybe it can help point, like a lighthouse, it can sort of flash and say, you should look this way, this would be interesting. So it's just one way that we can integrate more sophisticated machine learning algorithms into our data analysis. And that is all.
Okay, thank you very, very much for the talk, Clara. So what we're going to do now is ask some, I'll go through the questions from the chat, and then at the end of that, what we can do is we can unmute everybody and we can show our appreciation for this fascinating talk and insight into what's happening. So what I'm going to do is ask the questions in the order that they've been asked. And so the first question is from David, and it's, can you advise about the various parameters you can affect in the local, so locally? So you mentioned the energy of particles, so how fast you can make them go. Are there other ways you can make it different?
Yeah, absolutely. So this is a very good question, and there's a whole sector of physicists who are dedicated to this, answering this question. So you can decide on the energy that you collide at. You can also decide how dense or how not dense the particles, the protons, are compacted together in what we call bunches. So the LHC is not a continuous stream of particles. We bunch them together, and it's every time these bunches cross that we hope to get collisions. You can also change the angle that they come in at. So this is sometimes intentionally done because, for example, LHCb doesn't want a lot of collisions to happen at once, whereas Atlas and CMS, I say we want as many to happen as possible. That's because we want to collect the data. But then it does make challenges in doing the measurements that we want to perform. So for example, we sometimes specifically ask the accelerator physicists running the LHC and the other accelerators to provide us with bunches that mean that we only get on average one collision per bunch crossing. And this allows us to do very precise measurements. So we don't collect as much data, but it does mean, for example, if we want to measure the mass of the W, to do this very precisely, the W boson, we really need nothing else to happen in our detector. So there are lots of different parameters that can be influenced, and actually the accelerator physicists love playing around. Their whole research is just to work on this in the accelerator, and they don't really care about the collisions. They want their beam to be as perfect as possible, or to be able to control it as well as possible. And actually the collisions just get in the way of them being able to do that. So yeah, we have a lot of magnets around the LHC that really focus the beam and control it in ways to make it, to precisely control the parameters. At the moment, what we're limited by in terms of energy is actually not how well we can control the beam in the collision, but it's the magnets that are around the LHC. So if we can develop stronger magnets, then we can go to higher energies. But 14 TeV is our highest collision energy that we hope to be able to get to. Maybe 14.5, I've heard rumors, but it depends on if the accelerator physicists are allowed to play at that energy. And when I say play, it's absolutely not, I wouldn't use that turn of phrase in any audience because people get a little bit concerned. But really the only concern that we have is that we don't want to damage our accelerator. That's the only, the system is set up in a very safe way that if the energy gets too much, it would actually just break one of the magnets, and then we would have a year of repairs to do, so.
Now, I mean, I must admit, just speaking personally, I have complete sympathy with the word play. I think we should all be trying to play in science and so on, and in our jobs if we can.
Yeah.
So the next question, because I'm going through them in order, I'm going to ask a question which maybe should be asked right at the very end. So it's from Joe McKenna, and who's complimentary about the talk and wants to know what you think is going to happen to CERN. So you said it's a 40-year-long project, but what happens after we're a little bit older? So
this is a question that hasn't been decided yet. So we are currently debating and discussing within the particle physics and the wider physics community what the future of particle physics will look like. So one proposed plan that recently got some support from CERN, but that doesn't mean it's what we're going to do. It just means that's what we're going to look into in more detail, is something called the Future Circular Collider. So this is like an LHC, which is 27 kilometers in circumference, and you make it 100 kilometers or 80 to 100 kilometers in circumference. So there are two ways, actually. I mentioned the magnets, but there are two ways to increase the energy of the collisions happening in the center of the detectors. Either we have stronger magnets, or we increase the circumference of the ring for hadrons. And so this is a proposed new accelerator that would actually end up being constructed underneath the lake in Geneva. That's the only way that it can fit in around all of the mountains. And so it's currently in a design phase where the construction and the feasibility are being explored. So it's something that a lot of people are very keen on, but we have to investigate that we can definitely do it. And then there are also a lot of people who are studying the simulations and the predictions of what kind of physics we can get out of this, because we have to be very conscious that if we are allowed to build a collider such as this from public funds, that we know, I mean, we're in an uncharted territory. This is the difference now between particle physics before the Higgs boson and particle physics afterwards. The Higgs boson was something that we could discover, that we knew that the LHC would either find or rule out completely, and both were very interesting situations to be in. But now we don't have that such strong direction. But I was talking about dark matter. We know that there has to be something to explain dark matter. It could be a particle, it could not be a particle. And the standard model doesn't explain everything. It's a very tenacious theory that is very well describes certain aspects of our universe, but it doesn't explain the weakness of gravity. It doesn't tell us why we have matter, antimatter, asymmetry. There's a lot of things that are still missing. And so that's why we're trying to find out where it breaks, essentially, find out where it doesn't explain the universe, and explore those areas. So the Future Circular Collider is one option. There's also an option for a linear collider. So you build a very, very long straight tunnel, and you can either continue with hadrons, which is what protons are, or you can use fundamental particles such as electrons, or even muons are being discussed. But we're really in a position now where it's not decided, and we have to come together as a community to understand where we're going next. There's also, China is discussing, although recent news suggests that it's gone lower down on their list of priorities, not really to do with COVID, but just that was the recent news. There was also Japan was talking about a linear collider. So it's an uncertain time, but that's also 20, 30, 40 years in the future, depending on the different projects. So we're upgrading the Large Hadron Collider to what's called the high luminosity LHC. And this is where we're really changing the parameters of the beam to collect as many collisions as possible, which is a challenge for me as someone who started on detector physics. So I was explaining how you measure the particles in the detector, and the more particles, the more collisions you have every bunch crossing, the messier the environment gets in the center of the detector, and the better the detectors have to be able to distinguish those particles. And also they have to be radiation hard. The particles, as they travel through the detector, can damage them, and we have to either design better detectors, or we have to design a way to be able to get them out and replace them with new ones. So there's lots of intermediate challenges as well that will keep us busy whilst we're deciding what to do for the future of particle physics.
Before I ask the next question on the list, I'd just like to ask one of my own, which is, I mean, you were just talking about the Higgs particle, and that it could have been there, it could have not been there. But of course, the question is also, there could be a Higgs particle, but not quite the Higgs particle of the standard model. Would you like to say anything about how much evidence or otherwise there is for a non-standard Higgs?
Yeah, none, sadly.
Ooh.
Yeah. So there's the supersymmetry theory that I mentioned before. One version of it has 5 Higgs bosons. So the one that we discovered would have been one of these, but then there would also be ones with slightly different properties. And so we're also measuring the Higgs boson's properties, the one we found, as precisely as possible to see if there are any other Higgs bosons of slightly different properties hiding in within that data. So far it's behaving exactly like a standard model Higgs boson. Yeah, we have a lot of presentations where we talk about our results, and every single one of them ends with, and this is very consistent with the standard model, and that's a very sad phrase to hear if you're trying to find new particles. Yeah. But it's why when the Higgs was announced, we didn't say we've discovered the Higgs boson. It was we have discovered a new particle consistent with a standard model Higgs. So the language is quite important to say that we don't know until we've measured all of its properties that it's exactly the Higgs boson predicted by the standard model.
Okay, thank you. So the next question is from Keith Denby. And he says, well, you know, the proton is made up of up and down quarks and gluons. Does the top quark have that sort of role? And if not, what is its role, if any?
So this is a very nice question. I like it because it's actually what's very interesting about the top quark. So all of the other quarks that we have form what we call hadrons. So this is where they combine into these composite particles, and they're very popular in LHCb to measure these different combinations of quarks in different states. But the top quark, because of its mass and therefore its lifetime, it actually changes into other particles, most likely a B quark, too quickly. And so it never forms these bound states, these composite particles. And that actually means that we can study its properties in ways that we can't measure the B quark, for example, because the B quark already is buddied up with other quarks to form either composite particles or what we call jets, where it's just a spray of hadrons in our detector, which is quite messy and very difficult to reconstruct. But this unique property of the Higgs boson in terms of quarks is one of the reasons it's so interesting. So yeah, it doesn't form, it doesn't group up with other particles the way that the other quarks do.
Okay, thank you. And then the next question is from Isa. So after the upgrade, I guess higher collision energies can be achieved. And what kind of particles or other discoveries are you hoping to get?
So yeah, so after the high luminosity upgrade, so not the upgrade that we're doing right now, but we're going to run for a couple of years and then we're going to shut down for a longer period to really upgrade the accelerator and the detectors. And yeah, there we're hoping to either go from 13 to 14 or from 13 to 14.5. It depends how much the accelerator physicists can play with their setup. And really, we don't have any expectations about what we will discover at this higher energy. It's not quite enough of a higher energy to necessarily expect a lot of new particles. Our theoretical predictions don't predict that something will suddenly come at this energy. But what it does mean is that some things that are rare, that are created quite rarely, will happen slightly more often. So it's not just about creating the particles, it's creating them with respect to other events that look very similar. And so really being able to distinguish what we're interested in from all of the other stuff that's happening in our detector. So this is why going to higher energies can help create some very rare events slightly more often. Because one of the tricky things about colliding protons is that if I collide 2 electrons together, I know exactly how much energy I've given this electron, and I know exactly how much energy I've given this positron. And when they collide together, I know exactly how much energy is in that system, and therefore the likelihood of creating a certain particle, we can see in our graphs that as we slowly increase the energy, suddenly there's a jump in a new particle created. The thing about protons is that that diagram I showed you, they're so messy. They've got 3 quarks inside of them, they've got gluons, and they've got a whole bunch of other, what we call C quarks, sort of quarks that are existing and then not existing. And we don't know, we can never truly know which of those particles inside of the protons were involved in the collision. So we don't know how much energy this system has when the protons collide. So we don't get these beautiful increases in production of certain particles. So it's a very brute force method. We just have to collide and collide and collide and collect all of the data. And then when we've collected the whole heap of data, then we start using our sophisticated selection techniques. And this is why I'm interested in machine learning, because it's a lot of work to go through every individual event and say, this one maybe, this one not. So if I teach a machine algorithm to go through it for me and to start to look for things that perhaps I don't notice looking globally, but the computer can look for patterns that could hint that there's something new that's happening there. So we're not necessarily expecting, but if there is, fantastic. I'd be very happy if we go to 14 TeV and suddenly there's a bump in our measurements. But it also allows us, what's very interesting about changing the collision energy is that we can compare, our theoretical predictions say at 13 TeV it should happen at this rate, and at 14 TeV it should happen at this rate. And we can measure the 2 of them and we can compare if both of them are correct. And if there's any differences, that might hint that there's something that's come into play, maybe at the higher energies. So it's a complicated way to do it. I'd love to do all these measurements with a nice lepton collider at a few TeV, and then we can do really precision measurements without any of the mess. But I guess all of this mess keeps a lot of us busy too, so I'm not complaining about having a job to do. Yeah, so it's a very, very waffly long answer to say that we don't know, and that we just have to keep collecting the data and hope to find something new.
Okay. Well, the unexplored future, you're going to explore it. So then the next question's from Dudley Tolkien, and so he's fascinated that the known fundamental particles in the standard models are something like 20 levels of magnitude larger than the Planck length. How much theoretical energy is dedicated to answering this? How realistic are answers in coming centuries? So I'm trying to understand quite what the question means, but I guess it's how far can we actually go to much higher theories? And it's like you were saying about gravity, that the LHC is not really testing gravity.
Yeah, and maybe Dudley, you can nod or shake your head if I'm going in the right direction. But I think when we get to the Planck scales, we're getting this unification of all of the forces. Ideally, they would meet at this scale, but actually when we extend the predictions at higher energies, some of these fundamental forces actually cross. And that's one of the beautiful things about the supersymmetry, is that it fixes this problem and just shifts these lines so that they meet at this point. But you're right, there's this whole chasm of missing we have the particles and then we have the Planck scale, and there's a whole section missing in the middle, but it will be a very long time before we can explore this area, and we would really need, so I've heard a fantastic suggestion of putting a collider on the moon, or even of ways of viewing astronomical. This is now getting more into science fiction, but I heard great suggestions that one way we could find out if there were aliens out there is that they would be doing this research the way that we are, and that they might be influencing astronomical bodies to produce high energy particles to be able to study at these energy levels, and that we could maybe see hints of this in the stars, and then that would tell us, hey, there's a particle physicist over there. That must mean that maybe there's some intelligent life. I'm not making any claims considering some of my colleagues, but what I mean is that if you can really influence your environment so much, then that would be a hint to us. But what we can really study on Earth is limited. We could put a whole collider around the Earth, but I don't know if we'd be allowed to do that.
Yeah, that would cost a bit.
Yeah, but it's a really interesting, but it goes more towards the way that Einstein used to have thought experiments. We have to, we can't yet test it experimentally.
And the next question is from Nigel from North London Humanists, who thanks you for the talk. And he'd like to ask, I think, really about sort of the quantum level of the theories and the physics that you're measuring.
Yeah, so it gets almost philosophical, because the idea of whether particles are actual particles or whether they're waves. I mean, when I was talking about the Higgs boson, the Higgs boson is an excitation in the Higgs field. So we can think of it as a particle, but really it's a fluctuation in the field at that point. And it's the same for all particles. So photons are excitations in the electromagnetic field. And that's why they can both act as a particle and as a wave at the same time. And so I think, so all particles have this duality, but it's really difficult to measure it in the same way that we could measure the wave particle duality of an electron. To be able to measure that for a Higgs would be a very interesting, but I can't think of a way that we could do it. So it's a very, it's a good philosophical question, but I can treat them as particles, and so that allows me to do the work that I'm doing.
Yeah, I think the wave particle duality test I've heard of is the double slit experiment with buckyball molecules has been done in Vienna, which I thought was wonderful. You know, something as large as that.
Yeah.
So I just another question, if I may. So, you know, your work on 4 top events, at the new run, are you expecting that to be dramatically different, or are you hoping you might get a discovery out of it?
So what I'm hoping for in the next run is that we can collect more data. So the thing that was really limiting us to the measurement that I was talking about, because actually we took the 4 tops and we split them into 2 sets. So one set is where the top quarks change into 1 lepton or 2 leptons that have the same electrical charge. And then the other set is where it changes into lots of leptons. And the chances of the top quark changing into leptons is lower, which means the amount of data we have in this set is smaller. But it's a much cleaner event, because as I was saying, for example, the muons are much easier to measure in our detector. So for this data set, we really want to collect more data. And it was very interesting to have this slight fluctuation in the number of events that we measured. And CMS, for example, which is why I was talking about CMS as our sibling experiment, didn't see this fluctuation. So they measured it at the rate that was expected. So when we collect more data during the next run, we can compare, do we still get this fluctuation? Does CMS not get the fluctuation? Does it eventually even out so that we both get the standard model prediction? Or there could be, I mean, it's not impossible that the fact that we see something that CMS doesn't, it could be down to the way that we have selected our data and the way that our detectors measure these particles. So what it will really help us do is to more precisely understand this data set. And yeah, so hopefully we then can push it over into this 5 sigma. There's also this other half of the data set that I was talking about that we're still working on, because it has so much background that it's very difficult to distinguish the events that we're interested in from the other events. And so hopefully we can improve. This one is more about improving our algorithms, improving our simulations. So more data is helpful, but not really the limiting factor in this data set. And then hopefully we stick them all together, and then we can say, yeah, we're really confident that we have observed this process. And it's the first time that it's ever been observed, well, at the LHC and ever.
Well, with that, we're going to bring the Q&A to an end. I'd like to thank you very much. And I'd like to also remark that as well as giving us an insight into how difficult this science is, I think also it was very good that what you did was you also talked about the different types of people involved, things like accelerator physicists, you know, the engineers, even the lawyers at CERN. You know, people from a huge number of backgrounds have come together to do this. And I think it was very good that you brought that out.